Hello everyone. In this video, I have discussed the valence bond theory of coordination compound. If you find my videos helpful, then please like and subscribe to my channel. Let's get started. Valence bond theory was developed by Linus Pauling. This theory explains the nature of bonding, geometry in three-dimensional space, the electronic structure of central metal atom or ion, and magnetic property of coordination complexes. The main postulate of VBT are: the central metal must have an empty orbital with suitable energy available for bonding, and the ligand must have a lone pair of electrons. The empty s, p and d atomic orbital hybridize together to form an equal number of new orbital of equivalent energy and definite geometry called hybrid orbitals. The total number of hybrid orbitals formed is the coordination number of central metal atom or ion. The fully filled orbital of ligand overlap with the empty hybrid orbital of the central metal to form the ligand metal coordinate bond. If the inner d, that is n-1 d orbital, are involved in the complex formation, then the complex is called inner orbital complex or low spin complex. If outer d orbitals, that is nd orbital, are involved in the complex formation, the complex is called outer orbital complex or high spin complex. Here I have tabulated a comparison of the inner and outer orbital complexes. In the inner orbital complex, the n value of the d orbital is 1 less than the value of s and p orbital, while in the outer orbital complexes, the 3 orbitals have the same value of n. For example, when 3d, 4s and 4p orbitals of 3d metal are involved in hybridization, give d2sp3 hybrid orbitals, which later overlap with the ligand to form an inner orbital complex. When 4d, 4s and 4p orbital of 3d metal are involved in hybridization, give sp3d2 hybrid orbital, which later overlaps with the ligand to form an outer orbital complex. Since in the inner orbital complex, unpaired electrons of inner d orbitals are involved in the formation, their complexes are low spin or spin paired complexes. While in the outer orbital complexes, unpaired electrons of inner d orbital remain unpaired. Their complexes are high spin or low spin or spin free complexes. Let us discuss 6 coordinate octahedral complexes first. In D1, D2 and D3 system, there are at least 2 vacant d orbitals, so they can form d2sp3 hybrid orbitals and can accept electron from the 2 ligand into their vacant hybrid orbitals. Therefore, these 3 systems always form an inner orbital complexes, irrespective of the nature of the ligand. In D8 and D9 systems, they don't have vacant inner d orbitals, so they always form an outer orbital complex through sp3d2 hybrid orbitals. D4, D5, D6 and D7 system can form an inner orbital complex when the ligand involves carbon or nitrogen donor atoms in the bond formation with metal. These 4 systems form an outer orbital complex when the ligand involves oxygen or halogen donor atoms in the bond formation with metal. A point to be noted here is that VBT didn't classify ligand as a strong field or a weak field ligand. They are just suggested that if the carbon or nitrogen donor atoms are involved, then the inner orbital complexes will form. And if oxygen and halogen atoms are involved, then outer orbital complexes will form. Okay, let's see D1 system. Example: hexaamine titanium 3 plus and hexa aqua titanium 3 plus. The atomic number of titanium is 22 and its oxidation state in this complex is +3. So the valence electronic configuration is 3d1 4s0, 4p0. It is already has two vacant 3d orbitals, so its excited state remain the same as the ground state. Now, the two vacant 3d 1 4s and 3 4p orbitals hybridize to give d2sp3 hybrid orbitals. Then the 6 ligand donate their sigma electron to empty d2sp3 hybrid orbitals to form an inner orbital complex. Both complexes or any other d1 system based octahedral complex have one unpaired electron, so they are paramagnetic complexes and their magnetic moment is √3 Bohr magneton. D2 system example hexaamine vanadium 3+ and hexaaqua vanadium 3+. The atomic number of vanadium is 23 and its oxidation state in this complex is +3. So the valence electronic configuration is 3d2 4s0 4p0. It already has two vacant 3d orbitals, so its excited state remain the same as the ground state. Now the two vacant 3d 1 4s and 3 4p orbital hybridize to give d2sp3 hybrid orbitals. Then the 6 ligand donate their sigma electron to empty d2sp3 hybrid orbital to form an inner orbital complex. Both complexes or any other d2 system based octahedral complexes have two unpaired electrons, so they are paramagnetic complexes and their magnetic moment is √8 Bohr magneton. D3 system example hexamine chromium 3+ and hexaaqua chromium 3+. The atomic number of chromium is 24 and its oxidation state in this complex is +3. So the valence electronic configuration is 3d3 4s0 4p0. It already has two vacant 3d orbitals, so its excited state remain the same as the ground state. Now the two vacant 3d 1 4s and 3 4p orbitals hybridize to give d2sp3 hybrid orbitals. Then the 6 ligand donate their sigma electron to empty d2sp3 hybrid orbital to form an inner orbital complex. Both complexes or any other d3 system based octahedral complexes have 3 unpaired electrons, so they are paramagnetic complexes and their magnetic moment is √15 Bohr magneton. D4 system with strong field ligand like carbon or nitrogen donor. For example, hexaamine manganese 3+ or hexaamine chromium 2+. The atomic number of manganese is 25, so the valence electronic configuration based on its oxidation state is 3d4 4s0 4p0. It has one vacant 3d orbital while the ligand in these complexes are nitrogen donor. So rearrangement of the electron has to take place in the excited state to vacant two empty 3d orbitals. Now the two vacant 3d orbitals 1 4s and 3 p orbitals hybridize to give d2sp3 hybrid orbital. Then the 6 ligand donate their sigma electron to empty d2sp3 hybrid orbital to form an inner orbital complex. Both complexes or any other d4 system based 6 coordinate complexes have two unpaired electrons, so they are paramagnetic and the magnetic moment is √8 Bohr magneton. D4 system with weak field ligand like oxygen or halogen donor. Example hexaaqua manganese 3+ or hexaaqua chromium 2+. This is also a manganese complex and its oxidation state is also +3. The ligand in this complex are oxygen donor, so excited state remain the same as the ground state. Now one vacant 4s, 3 4p and 2 4d orbitals hybridize to give sp3d2 hybrid orbitals. Then the 6 ligand donate their sigma electron to empty sp3d2 hybrid orbital to form an outer orbital complex. Both complex or any other d4 system based octahedral complex of weak field ligand have 4 unpaired electrons, so they are paramagnetic complex, and the magnetic moment is √24 Bohr magneton. D5 system with a strong field ligand like carbon or nitrogen donor. Example, hexaamine iron 3 plus or hexaamine manganese 2 plus. The atomic number of iron is 26 and its oxidation state in this complex is +3. So the valence electronic configuration is 3d5, 4s0, 4p0. It has no vacant 3d orbital, while the ligand in this complex are nitrogen donor. So rearrangement of the electron has to take place in the excited state to vacant 2 empty 3d orbitals. Now the 2 vacant 3d orbitals, 1 4s and 3 4p orbital hybridize to give d2 sp3 hybrid orbital to form an inner orbital complex. Both complexes or any other d5 system based octahedral complexes of a strong field ligand have 1 unpaired electron, and so they are paramagnetic complexes and their magnetic moment is √3 Bohr magneton. D5 system with weak field ligand like oxygen or halogen donor. Example, hexa-aqua iron 3 plus or hexa-aqua manganese 2 plus. This is also an iron complex with oxidation state +3. The ligand in this complex are oxygen donor, so the excited state remain the same as the ground state. Now the 1 vacant 4s, 3 4p and 2 4d orbitals hybridize to give sp3d2 hybrid orbital. Then the 6 ligand donate their sigma electron to empty sp3d2 hybrid orbital to form an outer orbital complex. Both complexes or any other d5 system based octahedral complexes of weak field ligand have 5 unpaired electrons, so they are paramagnetic complexes and their magnetic moment is √35 Bohr magneton. D6 system with a strong field carbon or nitrogen donor ligand. Example, hexaamine cobalt 3 plus or hexaamine iron 2 plus. The atomic number of cobalt is 27 and its oxidation state is +3. So the valence electronic configuration is 3d6, 4s0, 4p0. It has no vacant 3d orbital while the ligand is nitrogen donor. So the rearrangement has to take place in the excited state to vacant 2 empty 3d orbitals. Now the 2 vacant 3d orbitals, 1 4s and 3 4p orbital hybridize to give d2 sp3 hybrid orbital to form an inner orbital complex. Both complex or any other DC system based strong field complex have no unpaired electrons, so they are diamagnetic with 0 magnetic moment. DC system with weak field ligand like oxygen or halogen. Example, hexa-aqua cobalt 3 plus or hexa-aqua iron 2 plus. This is also a cobalt complex and its oxidation state is +3. So the valence electronic configuration is 3d6, 4s0, 4p0. It has no vacant 3d orbital while the ligand is oxygen donor. So excited state remain the same as the ground state. Now 1 vacant 4s, 3 4p and 2 4d orbitals hybridize to give sp3d2 hybrid orbitals. Then the 6 ligand donate their sigma electron to form outer orbital complex. Both complex or any other D6 system based weak field ligand complex have 4 unpaired electrons, so they are paramagnetic and the magnetic moment is √24 Bohr magneton. D7 system with a strong field ligand. Here the oxidation state of cobalt is +2, so the valence electronic configuration is 3d7, 4s0, 4p0. It has no vacant 3d orbital while the ligand in this complex are nitrogen donor, So rearrangement of electron has to take place to vacant two empty 3d orbitals. Now the two vacant 3d orbitals, one 4s and 3 4p orbital hybridize to give d2 sp3 hybrid orbitals. However, the electron occupying in the 4d orbital is high in energy. So the complex of cobalt plus 2 is not stable with strong field ligand like carbon or oxygen. Hence, its inner orbital complex is not known to be stable. This is why cobalt plus 2 in hexaamine cobalt plus 2 get easily oxidized to cobalt plus 3 to form a stable hexaamine cobalt 3 plus complex. D7 system with weak field ligand. Example, hexa aqua cobalt 2 plus. The oxidation state of cobalt is plus 2. So the valence electron configuration is 3d7 4s0 4p0. Since the ligand is oxygen donor, so the ground state as well as electron excited state remain the same. Now the one vacant 4s, 3 4p and 2 4d orbital hybridize to give sp3d2 hybrid orbital. Then the 6 ligand donate their sigma electron to form an outer orbital complex. This complex or any other d6 system based 6 coordinate complex of weak field ligand have 3 unpaired electrons, so they are paramagnetic complex and the magnetic moment is root 15. D8 system with weak field ligand like oxygen or halogen. Example, hexa aqua nickel 2 plus. Likewise, cobalt plus 2, nickel plus 2 also doesn't form a stable complex with a strong field ligand. Hence, its inner orbital complex is not known to be stable. The atomic number of nickel is 28 and its oxidation state in this complex is plus 2. So the valence electronic configuration is 3d8 4s0 4p0. It has no vacant 3d orbital while the ligand in this complex is oxygen donor. So excited state remains the same as the ground state. Now one vacant 4s, 3 4p and 2 4d orbital hybridize to give sp3d2 hybrid orbitals. Then the 6 ligand donate their sigma electron to form an outer orbital complex. This complex or any other D8 system based octahedral complex of weak field ligand have 2 unpaired electrons, so they are paramagnetic and the magnetic moment is root 8 Bohr magneton. D9 system with a weak field ligand. Example, hexa aqua copper 2 plus ion. Likewise, cobalt plus 2 and nickel plus 2. Copper plus 2 also doesn't form a stable complex with the strong field ligand. Hence, its inner orbital complex is not known to be stable. The atomic number of copper is 28, oxidation is plus 2, so the valence electronic configuration is 3d9 4s0 4p0. Since oxygen is the donor, so excited state remain the same. Now one vacant 4s and 3 4p and 2 4d orbital hybridize to give sp3d2 hybrid orbital, which later on accept electron from the ligand to form an outer orbital complex. This complex or any other D6 system based D9 system based 6 coordinate complex has 3 electron, 1 electron, so they are paramagnetic and the magnetic moment is root 3 Bohr magneton. Okay, now let us discuss 4 coordinate square planar and tetrahedral complex. In D1, D2, D3 and D4 system, there is at least one vacant d orbital, so they can form dsp2 hybrid orbital and can accept electron from one ligand into the vacant hybrid orbitals. Therefore, These four systems always form an inner orbital complex, that is square planar complex. D5, D6, D7, D8 and D9 system can form DsP2 inner orbital complex when the ligand involve carbon or nitrogen donor in the bond formation with metal. These four systems form sp3 outer orbital complex, that is tetrahedral complex, when the ligand involve oxygen or halogen donor atom in the bond formation with the metal. Okay, consider D5 system with strong field ligand carbon or nitrogen donor. Example, hexacyano manganese charge 2- ion. The atomic number of manganese is 25 and its oxidation state in this complex is +2. So the valence electronic configuration is 3d5, 4s0, 4p0. It has no vacant 3d orbital while the ligand in this complex are carbon donor. So rearrangement of the electron has to take place in the excited state to vacant one empty 3d orbital. Now one vacant 3d orbital, one 4s and two 4p orbitals hybridize to give dsp2 hybrid orbitals. Then the 4 ligand donate their sigma electron to form an inner orbital complex. This complex or any other complex of D5 system based 4 coordinate complex of weak field ligand have 3 unpaired electrons, so they are paramagnetic and the magnetic moment is √15 Bohr magneton. D5 system with weak field ligand like oxygen and halogen. The atomic number of manganese is 25. Again, oxidation state remain the same. So the valence electronic configuration is 3d5, 4s0, 4p0. It has no vacant 3d orbital, but the donor is halogen, so no need to do any rearrangement in excited state. Now with the one vacant 4s, 3 4p orbital hybridized to give sp3 hybrid orbitals. Then the 4 ligand donate their sigma electron to empty sp3 hybrid orbital to form an outer orbital complex. This complex or any other complex of D5 system based tetrahedral complex having weak field ligand have 5 unpaired electron, so they are paramagnetic and the magnetic moment is √35. There are some limitations of VBT. Number 1, this theory failed to account for the characteristic electronic spectra of coordination compound, that is, it cannot explain the color of complexes. For example, you can consider these complexes of nickel. All the 3 are 6 coordinate complexes possessing octahedral geometry and have same central metal ion, but they show a color variation. VBT cannot explain this color variation. This theory considers only the magnetic moment by spin and does not consider the orbital motion of electron. As a result, there is a difference in mu s and mu experimental value of many complexes. Here I have tabulated the transitions metal with their spin value magnetic moment and the experimentally observed one. As you can see, there is not only a difference in the magnetic moment of a spin value with the observed, but experimentally a variation in the magnetic moment is also observed. It does not explain why same metal ion in the same oxidation state form outer orbital complex with highly electronegative ligand but inner orbital complex with less electronegative ligand. D4, D5, D6 and D7 system based metal ion form outer orbital complex with highly electronegative ligand like oxygen and halogen and form inner orbital complex with less electronegative ligand like carbon and nitrogen. According to VBT, all the square planar complexes of nickel plus 2 should be diamagnetic, but actually some square planar complexes of nickel are paramagnetic too. Look at this table. VBT cannot explain first and second complexes. The third complex, which is tetracarbonyl nickel, have carbonyl ligand, so it should be dsp2 hybridized, square planar and diamagnetic. However, this complex is sp3 hybridized, and if it is sp3 hybridized like the first one complexes, then it should be paramagnetic. This cannot be explained by VBT. Look at the first complex, tetrachloronickel 2 ion. The atomic number of nickel is 28 and its oxidation state in this complex is +2. So the valence electronic configuration is 3d8 4s0 4p0. It has no vacant 3d orbital, while the ligand in this complex are chloride donors. So excited state remain the same as the ground state. Now the one vacant 4s and 3 4p orbital hybridized to give sp3 hybrid orbital. Then the 4 ligand donate their sigma electron to form sp outer orbital complex. This complex of weak field ligand has 2 unpaired electrons, so it is paramagnetic and the magnetic moment is √8. The ligand in this complex are cyanide donors. So rearrangement of electron has to take place in the excited state to vacant one empty 3d orbital. Now the one vacant 3d orbital, one 4s and 2 4p orbital hybridized to give dsp2 hybridization, which later accept electron to form inner orbital complex. This complex doesn't have any unpaired electron, so it is diamagnetic with the magnetic moment of 0 Bohr magneton. The oxidation state of nickel in this complex is 0. So the valence electronic configuration is 3d8 4s0 4s2 4p0. The ligand in this complex are carbonyl, so rearrangement of electron has to take place in the excited state to give the valence electronic configuration of 3d10 4s0 4p0. Now the one vacant 4s orbital and 3 4p orbital hybridized to give sp3 hybrid orbitals, which later accept electron from the carbonyl to give a diamagnetic complex with tetrahedral geometry. Now I end this video here. Thanks for watching. Please like and subscribe to my channel.